Hello there. I'm Morrison Ricard, and I will be presenting my project on Quasi 1D nozzle flow. So the idea is that we have a nozzle where a fluid enters at a subsonic speed at the inlet. It's accelerated to a supersonic speed, and that is where it leaves. And at the middle, the throat, where the nozzle is at its tightest point, the Mach number is 1. This is an important aspect as we'll be using it to verify our results later on. If the Mach number is 1 at the throat, we know that everything has gone correctly and that the simulation has been properly modeled. So here we're going to take a look at the code. At the top we have the governing equations. All of these D's represent partials, and this is non-dimensionalized. So rho is the density over the initial density. V is the velocity over the speed of sound. The area is the area over the area of the throat, and the temperature is the temperature over the initial temperature. So we have the partial density with respect to time is equal to negative density times the partial velocity with respect to x minus the velocity times the density times the natural log of the area with respect to x minus the velocity times the partial density with respect to x for our continuity equation. For the momentum equation, we have that the partial velocity with respect to time is equal to negative the velocity times partial velocity with respect to x minus 1 over lambda times the partial temperature with respect to x plus the temperature over the density times the partial density with respect to x. For our last equation, the energy governing equation, we have that the partial temperature with respect to time is equal to negative the velocity times the partial temperature with respect to x minus lambda minus 1 times the temperature times the partial velocity with respect to x plus the velocity times the partial natural log of the area with respect to x. So this part of the code here sets the initial conditions that we'll be working with. We were given a file with initial conditions. And so what it does is it reads in the data and sends all those conditions to their respective variables. So we have the x for the x over L ratio across the nozzle, the area, the density, velocity, and time for the first time iteration. I then calculate the natural log of the area because that's needed for the governing equations. This is lambda, which is also given. And for the MacCormack method, the time step needs to be equal to c times delta x over the square root of t plus v. For this case, I'm using c as 0.5, as the case for stability is is less than or equal to 1. So at 0.5, I should be safe with the simulation being stable. And here I just calculate a bunch of steps in case the model doesn't actually go to plan. It will still end up reaching a place we can call a solution if it doesn't end up reaching steady. So it's kind of just a backup in case things go south. So this is just to plot the initial conditions, which I will show right now. So here are the initial conditions versus what ends up being the final conditions after everything is calculated. We can see that these all end up being quite varied through the process of the simulation, but that is good because these are all essentially just estimates, and through this MacCormack process, we get them to this point. We know it's not correct because the Mach number of the throat is much larger than 1, but that's okay because if it was less than 1, we couldn't use it. These governing equations and everything wouldn't work because there'd be some sort of shock in the system. But since it's greater, we can use it, and we can see that it does end up being 1 at the end. So going back to the code, after that, I just list the boundary conditions. So at the subsonic side of the inlet, the density is equal to the initial density, the temperature is equal to the initial temperature, but we don't exactly know the velocity, so we have to extrapolate for that. On the supersonic side, everything has to be extrapolated because nothing there is held constant. So getting into the actual MacCormack method and solving this, we create a bunch of vectors that just are there as placeholders for now to keep the simulation from getting angry, because I start at the x equals 2 because I can't calculate the points at the boundaries. That's what the boundary conditions are for. So we start off by calculating a forward difference for whatever the values we have, starting at the initial times. And we just use a forward difference to calculate all the partials with respect to x. Using these partials in our differential equations, we calculate the partials with respect to time for that time. We then take a predicted step forward using the current value times the partial with respect to time times our time step. Applying boundary conditions at the first and last points fills up the predicted vectors with all of their values. We then take a rearward difference across all x at these predicted values for our partials, and then we calculate the slopes again using the partials with the rearward differences at this future time, this predicted time. Then the average of the slopes is found. So we take the slope found at the initial values and then the slope found at the predicted values, and we divide it by 2. We then take the values that we have and add the actual slope, the averaged slope times delta time, the time step, to get our future values at the next iteration for all the interior points. The boundary conditions are then applied to get the first and last points. And now, since delta t is a function of variables that vary with x and time, it has to be calculated again so that we make sure the system doesn't explode. So that's just done again, where we calculate it for all x's and then take the minimum to be safe. Here I'm calculating the change, so the change in the future value minus the initial value. And once this ends up being 0, we know that we've reached steady state. So there's no point in doing a bunch of extra iterations. It'll cancel out the loop, and then it will plot our final results, which we have over here. So we can see that it's 0.994 for the Mach number at the throat, which is close enough to say it's 1 and that everything has gone correctly. You can see it comes in subsonic, gets slightly increased, and then once it hits there, it's now supersonic, and this is where it leaves. The density actually goes down as the fluid gets accelerated. The same thing happens for the temperature. The velocity goes up though, because the whole point is to accelerate the fluid, so it must be moving faster. And that is it for the standard conditions. I did, however, go in and vary the initial conditions because I wanted to see how this model would react to that. So I took this part here. We're taking the initial density ratio at the inlet and changing it. So I have a vector here that has a bunch of different values, and using an equation that was used to calculate the initial conditions, I replaced the 1 with one of these values so that at the inlet, the density ratio, or the normalized density, is actually different than what it should be, just to see what would happen to the simulation. So it goes through and it runs it for each one of these different ones that I've chosen. And then down here, it plots those all as well. So I will show those plots now here. And we get some interesting results. So we can see right off the bat that for 0.75 and 0.5 of the standard ratio, we get these results that obviously have broken the model. They're dipping into the negatives for Mach numbers. They're flying all over the place. We've got infinite slopes all over here. And so we can tell that it just obviously, we can't take these values as being anything that could be real. For anything above that, though, the Mach number actually stays the same. The profile is the same. It's still 1 at the throat. And the velocities and the temperatures are also the exact same. The densities, they start at whatever their initial ratio was, and they actually end up converging to the same point at the very end. That was just one of the conditions that I varied. Another one was the temperatures. So I actually went in here and did the same thing for that, where I varied the initial temperature ratio. And following the same situation where I take the equation for initial temperature and I vary that with these values. And the velocities were actually dependent on that. So those the initial velocities are set in the same way. And it goes through and it solves using the MacCormack method again, and then plots, which I will show you here. So here we've got these plots, and we can see that actually the model didn't break until the ratio was 0.5. We can see it's obviously broken again because this is dipping into negative Mach numbers and bouncing up and down. So obviously something's gone wrong, but for 0.75 and above, the Mach profiles stay standard with being 1 at the throat. The densities actually don't change, the distributions are all the same, but the velocity distributions and the temperature distributions are the ones that vary. So the temperature distributions, they start at whatever their varied value was at the beginning, and they end up going down like is seen over here, but they don't end up converging to the same point. They're still offset by a bit with the higher and ratio being a bit higher. So that makes sense why the velocities all start at the same point, but then at the end, they end up becoming offset. Because if the Mach number is the same here at the end, then if the temperature is increased and our Mach number for this is v over the square root of t, then the velocity would also have to increase to keep that Mach number to be the same. So that's why we see these offsets here at the end. The last thing I varied in the simulation was the position of the throat, so that point that is narrowest in the nozzle. And again, it's the same thing where I take a vector and I have a bunch of variations, use that, and use an equation that was used to calculate the initial conditions, goes through and it runs through the MacCormack method again and plots the results again. And here we have those results. So we can see here the system actually never completely blows up and gives us crazy results. It just seems to shift, which would make sense as I'm simply just shifting the throat left and right across. And so here when the throat is 2, we get the Mach number is 1 at 2. Here when the throat is at 1.75, in between 1.8 and 1.7, we can see that the Mach number is 1. Again here, with it being at 1.4 or 1.6, it is 1, if it will, there it goes. And then here for below that, it's 1 again. Same thing over here, between 1.2 and 1.3, we can see it's 1. And here at 1, it is again 1. So it just shifts back and forth where I shift the throat at. So say we put the throat over here at 1, we shift it farther to the left. The density decreases faster because we can see over here the density decreases as it's getting towards that throat. So if we put the throat farther to the left, well then the density is going to have to decrease first, and it's going to decrease faster, as opposed to it being at the right and decreasing slower. But what's interesting is they do all converge to about the same point. For the velocities, it's a similar story where we see that the velocities increase as they approach the nozzle. So putting the nozzle farther to the left would cause them to increase faster, and putting it farther to the right would cause them to increase slower. These also converge to about the same point. There's a bit more variation here though. The temperatures, it's again similar. As they decrease as they get towards the nozzle, so putting it to the left means they decrease faster. There seems to be the most variation here out of all of the variables besides the Mach number, and that would probably explain why there is more variation here, because it is a function of the variation here, the velocities and the temperatures. So since those are both varied, it adds up to this bigger offset here at the end. So it also makes sense because if the fluid is accelerated faster with the nozzle being closer, it would end up being faster at the end because it's had a longer time to be moving at a faster speed and keep accelerating. So that would explain that, and as well as if the throat was moved to the right, it would end up at a lesser speed when it exits because it hasn't been accelerated as quickly. I just really thought it was interesting that I could mess with these parameters, and the situation wouldn't blow up. It would just keep its same general shapes for all of the distributions, and it would just work fine and move along as the throat moved. But that is the end of my presentation. I hope you enjoyed. Thank you.